This experiment is to test the sensitivity of a cell phone accelerometer. I am using the Android Bubble Level Pro app. This is the second experiment. The first time a Moto Z Force was used. This time we'll be testing the Galaxy S5. The phone will be mounted on a 7-day circular chart recorder. I drilled a hole in the side of a board and secured it to the chart recorder spindle with a locking screw. Here is video of the setup and of the test in progress. The Bubble Level app has a set button to calibrate the level at the start. Here I am doing that. Here is a screenshot of the start of the test and of the conclusion of the test. The test ran 2 hours, 7 minutes, or 2.12 hours. The 7-day circular chart recorder rotates at 2.14 degrees per hour. The recorder's rotation during the test is 2.14 degrees per hour times 2.12 hours equals 4.54 degrees. The droid's y-axis final reading was 4.8 degrees minus the 0.2 degrees starting point, which equals 4.6 degrees total rotation measured. The measured result is only 0.06 of 1 degree over the expected result. This is exactly the same result as when testing the Moto Z. This test has demonstrated the extraordinary sensitivity of the cell phone's micro electromagnetic system accelerometer, measuring a rotation rate of 7 times slower than the heliocentric model's alleged globe rotation. What follows is the complete test at 3 times speed, the technical portions of the RANIC video, plus commentary by GLOBEBUSTERS.
today's video, we're going to be looking at the MPU 6050 6 degrees of freedom breakout board, which features a 3-axis accelerometer and a 3-axis gyroscope. So I'm going to be walking you through the entire implementation of this particular integrated circuit. I'm going to be showing you exactly which registers I'm pulling the data from, exactly how to wire and write the software to be able to read the values, what to do with the values, what you can possibly modify in the program to kind of get something relevant more than just the pure raw data of the accelerometer and the gyroscope. And as a very quick demonstration of the data that's currently being sent back to the Arduino serial port, you can look on your screen right now, and as you can see, you have the gyro readings in the G's as well as the accelerometer readings in G's. So let's take a look first of all at the gyroscope. It is the speed at which you rotate above a certain axis. So imagine my Z axis is going straight into the table. So if you look at your screen right now, the Z is about 0.4 degrees or so. So that's the error that we're getting. As soon as I start rotating the board, you see that number decrease because I'm going in a clockwise direction. If I go counterclockwise, that number is going to go up until I release the board. As far as the accelerometer goes, this is currently reading the G-force that is being exercised by Earth. So once again, this is in the Z-axis. You have 1G going down. If I tilt the module along the Y-axis, you can see this force is being spread evenly at 45 degrees on the Y and the Z axes.
how we should have been talking about gyroscopes all along.
Well, the thing the accelerometer picks up that's causing the issue is gravity. And so you come up with an accelerometer that's giving you one bit of data, and you've sort of got two unknowns. You've got one, which way is the gravity vector pointing, and two, which way is this thing accelerating. Now fundamentally we can make some assumptions that when you're starting out at thrust, this thing isn't moving. And then you can say, okay, gravity's down. We measure a little bit of acceleration incrementally. All right, we know we moved this way a little bit, so we can assume that gravity's pointing down this way. Now we go a little bit farther. All right, we know we moved it a little bit farther. Gravity's now this way. But you've got a little bit of tolerance on each of those measurements, and so as you go along, your gravity vector is getting less and less accurate over time, and so your readings are getting less and less accurate. What the gyro does is it just looks at angular rate. So sitting here, you're getting a 0. As soon as you move, you don't have to worry about the gravity vector. All you see is that you've changed an angle, and that gives you a lot more accuracy. Another problem with the accelerometer is that if it's positioned here, and we make a motion, we know the distance between the accelerometer and the pivot point approximately. And so we can tell how far our angle went. If we are doing something where the device is positioned like this and we're thrusting, now the distance is changing, and our angular measurement is becoming much more complicated. We have to know how far we thrust, as well as how much force has been applied. Where with the gyro, it doesn't really matter where the gyro is in the device. Tilt is tilt, and it gives us a result.
So it starts out with information that, I mean, the accelerometer starts out with information that we don't end up using except as a starting point to start calculating from.
Yeah, it's something we just need to subtract out fundamentally.
Right.
And it creates inaccuracies over the long run.
The space station provides a place to test many technologies in this space environment where they will be used. Lori Meggs with the station's Payload Operations Integration Center at the Marshall Space Flight Center in Huntsville spoke with Chris Provencher, a project manager with Ames Research Center. He described how his team on the ground controls the flight of robotic satellites on the station using a smartphone, similar to the ones many of us use every day.
So I'm researching smart spheres, which is a robotic free flyer on ISS. So the spheres are free-flying satellites on ISS, and they use CO2 propulsion to move around, and they can navigate, but they're satellites.
What kind of controller are we talking about?
So the controller is actually a Google Nexus S smartphone. So by connecting that smartphone to the satellite, we can use the Wi-Fi on the phone to communicate with the satellite via the LAN that's on board ISS. We can use the processors that are on the phone to control where the satellite goes and what it does. We can use the camera on the phone for vision, and there are other sensors on the phone that we can use as well.
So you send communication from the ground? You call the phone? How does that work?
Right, so a ground controller can communicate to the smartphone and tell the smartphone where to send the sphere. So that's how we control where this free flyer goes and what it does.
Have you had any results thus far?
Yes, so in December of 2012, we did do a demonstration where a ground controller in the Mission Control Center in Houston controlled the smart spheres to perform a mobile camera task. So he was able to uplink commands to the smart spheres to tell it where to go and where to take imagery. And he was able to not only run some autonomous plans that the smart spheres ran, but he was also able to interrupt the plans and take over manual control of the smart spheres. So it was very successful.
What did we learn from that?
Well, we learned that we can control a robotic free flyer from the ground under the supervision of a ground controller. The crew only has a limited amount of time on station, and a lot of that time is spent doing maintenance and housekeeping types of activities, to include moving cameras around and also doing other types of environmental surveys, such as taking noise level readings, radiation level readings, other things to make sure that the station is safe. But if we can offload those tasks to a robot, that will free up time for the crew to spend more time working on science.
And that's what's important to us.
That's what's important.
Why is the space station an ideal place to conduct this kind of research?
Well, there are a couple of reasons we want to do this on ISS. First, the ISS is the ideal test bed for working in microgravity with free flyers. And secondly, since we want these robotic free flyers to be deployed on the space station, we're actually doing our testing in the operational environment. The Smart Spheres is a prototype for a future free-flying robotic system. By using the smartphone, it allows us to control the spheres and to demonstrate the activities of a free-flying camera or a free-flying sensor. And so the lessons that we get from these tests will inform us on how to build the future system.
Yes, I'll just get this gyroscope here, and it's just a toy gyroscope really, but of course in zero gravity, if you knock it, it's going to tumble, it's going to move around like any object up here does. However, if I get this spinning, just give me a second. So once the gyroscope is spinning, you can just see how stable it becomes. And however I knock it, it's not going to change its plane. It's going to remain in the same plane. I can put it physically into a different plane and tap it again, but it will still hold that same plane, and it's much more stable. So it just gives you an idea of how we use spin stabilization and gyro stabilization for control on board the International Space Station.
Balls Out Physics, Episode 2, The Gravitational Constant. When I first discovered flat Earth theory, I thought I could debunk it right away. But the problem was I couldn't. I realized that there were some very good points being brought up by the flat Earth community, and that's why I started this series, because I'm really asking for help here. I can't explain these things, and I've got a pretty strong physics background. I took 2 physics courses in high school and then a bunch in college to get my degree, and maybe I'm missing something, maybe I'm not. But one of my favorite sayings in the engineering world is, you learn 10 times more from your mistakes than you do from your success. This is what we always tell rookie engineers. This is what they told me. Don't worry about making mistakes. Don't worry about being wrong. Because when you are wrong or you do make a mistake, you want to find out why. And on the way to finding out why, you learn a ton. So never be afraid to be wrong, because you can learn from it. And no one on this earth who has ever lived on this earth has ever been right all the time. All the time. It's never going to happen, and it's never happened. So accept it. Learn from it. So anyway, this episode is mainly about gravity, but it's about the gravitational constant in the gravity equation. However, to get there, we need to start with some basic physics. Newton were both Freemasons. It's a very big club, and back then, the average person couldn't even write their own name. So people slowly were introduced to the sciences. More and more people were introduced to the sciences over the years, and it wasn't just the wealthy people over the years. And I know there's a symbol out there that a lot of people have been trying to figure out. It looks something like this. You ever seen one of these before?
let's talk about what I'm sure a lot of people want to hear about. Darren did a couple of hangouts yesterday on this, and when I found this, I don't know, 3 or 4 days ago, I posted this video, mirrored it on GLOBEBUSTERS, and it is a video by a YouTuber by the name of Ranik, who is a very intelligent person, very, very interesting guy, and I'm sure everybody's seen this. If you haven't, by all means, watch it either on our page or on Ranik's page, or the multitude of other people that mirrored it, which is great, because this is really some damning evidence, in my opinion, and there are not really any very good explanations for a lot of this. But so what essentially we're being told here is that by virtue of the accelerometers in the phone, in iPhones, which use these MEMS devices, or micro electromechanical system devices, we are able to kind of set an attitude reference in free space, okay? And Ranik goes into detail about how this is done, and he also has some experts that are actually doing the coding and talking about it. It's very well documented, but it requires a little bit more about understanding how these sensor units actually work. And I'm going to play a little bit of a clip that just kind of covers in the most basic way how these accelerometers and these MEMS devices actually kind of work. And because honestly, I didn't know. I had no idea how they worked, so I had to look it up, and it's like, wow, that's really ingenious. And the great thing about it is that they truly are not using gravity to do this. Not for the gyros, not for the accelerometer or anything like this. It's basically, referencing it upon itself. So let's look a little bit at how these MEMS devices work, and this is just a couple minutes, but we'll play this, and it'll give you kind of a little bit of an idea of how this works, even though it's a little electronics, but nothing detailed.
Briefly explain how each of these microelectromechanical systems or MEMS sensor work. We will start with the accelerometer. It measures acceleration by measuring change in capacitance. Its microstructure looks something like this.
Okay, now let me explain this. What we see here is we see, this device that is basically flexible, and it's sitting on a set of springs. And we have the orange area charged in one polarity, and we have the green areas charged in another polarity. And when you get the two polarities closer and further away from each other, it literally will cause a change in voltage that's measured across these things, okay? So again, the accelerometers are not working by any gravity base, but they are working by what's called a capacitance change, or a charge change that's actually happening between the specific poles of the battery that's powering this particular device. So let me go ahead and move on.
It has a mass attached to a spring, which is confined to move along one direction and fixed outer plates. So when an acceleration in the particular direction will be applied, the mass will move and the capacitance between the plates and the mass will change. This change in capacitance will be measured, processed, and it will correspond to a particular acceleration value. Next is the gyroscope, which measures angular rate using the Coriolis effect. When a mass is moving in a particular direction with a particular velocity, and when an external angular rate will be applied, as shown with the green arrow, a force will occur, as shown with the blue arrow, which will cause perpendicular displacement of the mass. So, similar to the accelerometer, this displacement will cause change in capacitance, which will be measured, processed, and it will correspond to a particular angular rate. The microstructure of the gyroscope looks something like this. A mass that is constantly moving or oscillating, and when an external angular rate will be applied, a flexible part of the mass would move and make the perpendicular displacement. Okay, now let's explain how the magnetometer works. It measures the Earth magnetic field by using Hall effect or magnetoresistive effect. Actually, almost 90% of the sensors on the market use the Hall effect, and here's how it works. If we have a conductive plate like this and we set current to flow through it, the electrons would flow straight from one to the other side of the plate. Now if we bring some magnetic field near the plate, we would disturb the straight flow and the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means that if we put a meter now between these two sides, we will get some voltage which depends from the magnetic field strength and its direction. The other 10% of the sensors on the market use the magnetoresistive effect. These sensors use materials that are sensitive to magnetic field, usually composed of iron and nickel. So when these materials are exposed to magnetic field, they change their resistance. Okay, now let's connect the...
Okay, so basically what he's saying then is he's explained, the very basics of the operation of how this works. And so what he's saying then is that we're looking at these very, very minuscule detectors. And what's interesting about these things is these detectors are not much bigger than the width of a human hair, which astounds me. But, nevertheless, we know they work, and they are incredibly sensitive also. I had no idea that I was aware of the accelerometers, but I didn't know that they actually had gyroscope modules for this too. And when I heard that, I was curious as to how they worked. And it is so very simple. It's really astounding. So, and because of the fact that they are just differentiating a charge that's brought about by a change in EM field, it gives it a very, very high degree of sensitivity. Now, I haven't seen the specifications where it specifically, isolates what that sensitivity is, and I think probably there are some reasons why they wouldn't want to share that. Again, and this goes back to, like ring laser gyros and how they work, either differences in phase, in light waves that are going around in circles, or in this case, it's differences in minute voltage changes in the MEMS device. But the bottom line is because there are no mechanical, well, there are mechanical, but it's so small, but what they're really looking at is the electrical change that's going on within the mechanical device. So it's still not doing anything that has to affect the mechanical device so much as it manipulates the charge around it to be able to come up with a voltage differential that shows that change would be represented as an acceleration in the field. Okay, so it really is not referencing gravity, even though there is an absolute down that is programmed into it from the factory that cannot be changed. But what it allows us to do then is to be able to establish and record a position in free space, and lock that into the device with the phone. That's done by essentially calibrating your phone level or accelerometer, okay, and it remembers that. And then if you were to take it, somewhere else on the other side of the earth and turn it on, then theoretically you would naturally have a change in level, which would indicate curvature of the earth. But of course we know that doesn't happen, and it won't happen. For all of you that are going to do this experiment, you're going to find that it will not change at all. And it's interesting because you start thinking about that and you think, well, wait a minute, and because this is what I was thinking. You think about that and it's like, all right, so what is different between that and a level, right? Well, the level, of course, is this mechanical thing that you're actually seeing with your eye that is changing, because one side is higher than the other. So it's a purely mechanical thing as far as what you're visualizing and seeing. So I was thinking initially, Jaron, I don't know about you, but I was thinking, wow, so what you could do is just turn on that accelerometer and let it sit there, like you would a gyro, and there would be some sort of angular change in there, or not angular change, an angular change that would be represented by an acceleration vector that would be picked up by this accelerometer. But of course, we never see that, and we never will see that. So those of you that are going to do that experiment, you'll find, and of course, the reason we won't see that is because the Earth is not curved, nor is it moving. It's as simple as that. Now, the ballers are going to come back with a million other excuses as to why that works, but
gravity.
Well, yeah, gravity. and it's funny because they can't measure gravity. I don't care what they say, because if they could measure gravity, they wouldn't have to have these ridiculous LIGO apparatuses that depend on gravity waves literally physically changing the mechanical size of the laser canals, basically, that are having laser beams shot down them. And theoretically, supposedly, when the gravity wave passes through it, it physically changes the size of the chamber that the laser is being shot down in, and bada bing, you'd be able to detect gravity. Of course, that's just nonsense, because we have no examples of anything anywhere where strong electromagnetic fields physically alter matter. It just doesn't happen. There are no examples of that. So the whole premise of it is ridiculous in the first place, because there are no real world examples of that. So, from all the investigation that I've done into it and the way that I think about it, it seems like Rannick's point is absolutely right on the money. And we should see, if the Earth was truly a ball, we should see a difference in those level position as defined by the accelerometer, not by gravity, right? That's the whole thing. Gravity, nope, that's not what we're doing it by. We're doing it by essentially creating a reference to a change in attitude, which of course is measured by a voltage change like we just saw, in free space. So that's what it gives us. It gives us a reference in free space that we can actually lock in and record. And what we find is that down is down is down no matter what, and any angular change in the ball does absolutely nothing to it. Why? Because we're not on a ball. It's flat. Down is down is down. And we're not arguing that, because it's the same down here as it is in Australia. It's not upside down. It's the same down because it's flat. So this is just something that, you've got to really look into this. And this is something that I'm still definitely studying, because I was shocked. Honestly, you look at this and it's like, oh my God, we've had the answer to this, in our pocket virtually the whole time. And it's also interesting to see the coders talk about this as well. And of course, he goes over this in the video itself.
Yeah, I think it's unbelievable find, and it really, more than a find, it's kind of one of those wake up moments where I know David Weiss and I were talking about it for an hour yesterday, and Missa and I, and when you start kind of going over this in your head, it's just more evidence, more proof positive that it is impossible to live on a ball, that it's not even feasible. And so they've convinced us of a story, and we all kind of bought into it. And now to get away from it is tough, because we still run things by a globe model as if it could exist. And so really, when you start thinking about it, if you just lift up your phone and put it in that app that you're able to see, your change of level, if you just move it slightly to the left or slightly to the right, it goes off level. So if I put that down on the ground and I just let it sit there, well, it stays level the whole time. And you start thinking, okay, so why is it that I can't even go a little bit off and it moves that bubble? But by just setting it down, and that should tell you that we're not moving, we're not going any direction. And if somebody says, oh, well, the phone is reacting to gravity, well, that's what this video proves, is that the phone has no idea with forces what gravity is. Now, if somebody programs the phone from its inception to know that gravity is down, that's one thing. But ballers need to prove, in my mind, a big proof would be if you can show me that the phone knows gravity. But it does not know any gravity. It just knows where down is because it's been programmed that way. It doesn't have any force on the phone that is pulling on the phone. So when they make the phone, they set it on a countertop or whatever they're making it on, and they tell it that phone is the z-axis going to the floor. And then they lock that in. So that now that would be the same whether we lived on a ball or a vast plane, right? It's not going to change. The thing that would change is that in time, if you're spinning on the ball, that you would be changing your relative position to level. But that doesn't happen either. So again, this just comes down to they've made it a word salad, that if I'm standing on the beach in California and I'm standing on the beach, or somebody's in the beach in Australia, that we're both at sea level. And they've just convinced people that means you live on a ball, when we're both standing level. So you can't just replace that with, oh, it's because you're on a ball and you're both level. Well, no, they're underneath me. They can't also be level. And again, people can say, oh, you don't understand the way gravity pulls things to the center. Again, like Bob said, where is the evidence of any mass pulling anything to the center? So we're allowing them to get away with word salad and calling it science, where science needs to be repeatable, demonstratable, falsifiable. There is no falsifiable evidence you can come against the ball. Anything that you give, they'll just say, oh, well, you don't understand the way it works. You don't understand orbits. You don't understand gravity, whatever it is, but it simply doesn't work and can't be repeated and can't be shown. That's not science.
And it's not that hard to understand, people. I mean, they make it sound like you have to be a freaking PhD to understand the concept behind this. And the reality is you don't. It's not that difficult. They want you to think it's that difficult, but it's not. Okay? Rannick has made his case solid, not only with what he said, but with the documentation that he's used to back it up, including the programmers and the guy here that's describing it, you know, how this all works. And like I said, it's not that difficult to understand. It makes sense. The only thing that, you know, kind of confused me when I was looking at it was I wasn't exactly sure how the MEMS device actually worked. But now that I know how the MEMS device works, and I know that it's not a gravity-based thing, then this even makes more sense to me.